All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about ESP32 clock signals and ESP32 clock timing related stuff. I think at this point we are ready to continue with. Hold on, let me come back here. Yeah, at this point, I think we are ready to continue um, learning or relearning, or let's say we are ready to revisit LED PWM controller, which we visited this, or we first studied this when we were going through this entire Impel Rust for ESP32 book. We first came across this, and at the time I didn't know too much about actually, I didn't know anything about ESP32 clock signals. I didn't know anything about how the hardware reacts to clock signals in general. And this was what, maybe, I don't know, a week ago, 2 weeks ago, maybe. It feels like it's been 2 weeks, because in between I did also, actually, yeah, no, it's been 2 weeks, if not more, because in between I did also uh, take a little detour to learn stem draw, and I just kind of got busy with that. But yeah, I holy shit, it's been quite a journey. It's been a very informative journey, a very educational journey. So that's a good thing. Um, but yeah, now that I have a better idea of what now that I have a better idea, at least compared to before, of what is going on within the hardware, and how these clock signals are being generated, and what exactly are these various things that we were seeing over here. There's all of these formulas. So within these formulas, what exactly were all of these things that we were seeing? Now I have a much better idea. So that's great. That's awesome. I should find out how I can find the clock divider, because it says here it's the division factor for the clock source. Is this what we are specifying, or is this what's already like written down somewhere? Because I don't think we have a division factor by default. So, like, I don't know if we are meant to be reading this from, or if it's being read from some sort of register, or are we setting it? And then there's the resolution bits. There was a connection between this formula, the FPWM, and the res bits formula. There was a connection here that I'd found. I think it was more like, okay, if you have the clock signal, and um, I think that's the frequency, isn't it? Yeah, it's the frequency of the clock source. So if you have the frequency of the clock source, and you have the frequency of the PWM, and the clock divider, then you can calculate res bits. Or if you have the frequency of the clock source and the clock divider and the res bits, then you can calculate the frequency of the PWM. I think that was the relation between them. It's kind of like a voltage equals current multiplied by resistance, and then the relation between the three is that you can set it up in like a triangle kind of thing, and you can have, so let's say voltage is V, current is I, and resistance is R. So if you set that up in a triangle, you can say V equals IR, so I multiplied by R, I equals V divided by R, and R equals, would R be equal to V divided by I? I think so. I think so. Yeah, I think so. I'm not sure. But yeah, we're gonna continue with this. By the way, before we begin, real quick, I want to talk about something that I'm kind of excited to dive into, because this has actually saved one of my older systems. So I have this really old system that I've managed to keep alive thanks to Ubuntu. Um, this system is so old. Give me a second. Let me open up my chat on my phone, and then we can continue talking. Okay, so I have this really old machine. I have a couple of machines on which I'm running Linux. One of them is an incredibly old machine. The others are like relative. Well, I was about to say relatively new, but like I don't know. I don't know if you can still call them new, but they're within the last decade. This one system that I'm talking about is almost 2 decades old, if not more than 2 decades old. Uh, it's got it's got a dual core CPU, and it's got 2 GB of DDR2 RAM. Like that's how old it is. These days, I think we have DDR5 going on. I believe so. I believe we've got DDR5 going on right now. So this is a really old machine. And that being said, the RAM in it, if you're not careful, it can fill up really quickly. And because of that, I have had to switch over from a KDE Plasma desktop environment to i3WM, which is a window manager. And that was great. That was actually an amazing decision because um, it it definitely saved a lot of RAM, right? This specific machine that I'm talking about, I mainly only use it to watch Twitch, and Netflix, and once in a while YouTube, if there's something I want to watch on YouTube. Now, one problem that I run into is that the RAM can sometimes, fill up a little too much, and then the system becomes sluggish, and I have to close whatever tab is running. Usually, I try to keep only one tab active at a time, um, and that kind of conserves memory for the most part. But then I do have situations where, give me a second. I'm hoping we are not seeing. Oh shit, it's the same thing happening as yesterday. Yeah, dude, I don't know what to do about this. I actually didn't take the time to Google this yesterday. This glitch that's happening. Because I mean, Gemini was saying that it's happening because well, Gemini gave a couple of possibilities for what's going on, but um one of them was network congestion. And I can't tell what would be congesting the network right now. I mean, I didn't have this issue before, and on the machine on which I'm running this, I don't seem to be having that issue at all. Oh, sorry, on the machine on which the RTMP stream is being captured and then, streamed to the RTMP server, which is also running on that machine. On that machine, I'm not seeing any problems. The problems only seem to be occurring in uh, on this side when I receive the video feed. So I'm not really sure what to do about this. Um, I'm also not sure what some of these settings do. Um, Network caching. Give me a second. I'm just gonna ask Gemini real quick. Hey, in the VLC um, video source in OBS, what is the network caching setting doing? Think of network caching as as a shock absorber for your video system. Sorry, for your video stream. When you stream video over a network, data doesn't always arrive in a perfectly smooth, constant flow. There are tiny micro fluctuations in speed, which is jitter, or moments where a packet gets delayed. How it works: instead of trying to play every bit of data the exact millisecond it arrives, OBS/VLC creates a buffer, which is cached in the system's memory. The intake, the data arrives from the network and sits in this waiting room. Delay, if your cache is set to 1,000 milliseconds, OBS will wait until a full 1 second, um, until a full 1 second of your video, um, until it has 1 full second of your video stored before it starts playing the first frame. The playback, as it plays the stored video, it continues to fill the waiting room. Why it matters: if the cache is too low, 0 to 100 milliseconds, you get the lowest possible latency, which is real time. But if a single packet is late, the video will stutter, freeze, or give you that gray screen you saw earlier. Because the player has no backup data to show while it waits. If the cache is too high, 5,000 milliseconds, the video will be incredibly stable and smooth, even on a shaky Wi-Fi connection, but the feed will be 5 seconds behind real life. You know what? Okay, if that's the case, let's try this. Let's try setting this to 500 milliseconds and see if that solves the issue. Also, real quick, let me test and see how long that is. You know what? That's not that bad. That's really not that bad. Let's see if that fixes the issue. If not, then I can keep cranking up the setting. Okay, anyways, back to, oh, that did not help entirely. Let's try cranking it up further. Okay, let's say 2000 milliseconds. So 2 full seconds. Oh, actually, maybe I need to restart the stream. Well, restart the RTMP feed, I mean. Okay, so there is a slightly longer latency now, but let's see if the gray screen is still occurring. Okay, back to what I was talking about. What was I talking about? Yeah, what was I? Oh, yeah. So I was mentioning about this old system, and how watching Twitch, usually Netflix is fine, YouTube is fine. With Twitch, there's a bunch of other things being loaded. Um, I mean, to be fair, even with YouTube and with Netflix, also there might be a bunch of other like smaller programs being loaded, which we don't really know about because we don't need to know about them. But they're there. They're being loaded. They are what's, oh God, still. We're still getting this gray screen, dude. Okay, whatever. What was I saying? Sorry, I lost my train of thought. What was I saying? Yeah, yeah. So I when I try to load a Twitch live stream, right? It's kind of a 50-50 chance whether the live stream is viewable for me or not. What I mean by that is what could happen is um, I'll open up the live stream, the page will load, and a couple seconds in, the memory will start to fill up, and like big time fill up to the point that there's only maybe I don't know, 200 GB, sorry, 200 MB of memory remaining, 200 MB of RAM remaining. And that's bad because the entire system is gonna then struggle. So, well, 200, yeah, yeah, that would cause the entire system to struggle. So, um, what was I saying? Yeah, so I have to be mindful of which live streams I'm opening, which was unfortunate because there were certain live streams that I wanted to watch, but then I wouldn't be able to watch their stream on this machine because of that little memory filling up issue, and I never managed to narrow it down. I never managed to narrow down the cause because it would happen with some streams and it would not happen with other streams. And I mean, it would like, it's not like a random occurrence. It would consistently happen with some streams, and with other streams, consistently it won't happen. So I just couldn't watch certain streams, and um, that's why I decided to ask Gemini. And I had a conversation with Gemini about like ways that I can, because I was considering switching over to Lubuntu, which is meant to be a much more lighter weight Ubuntu, or Alpine Linux, which is incredibly lightweight, but it's not Ubuntu. It's its own OS. And before that, I wanted to ask Gemini if there's some ways that I can, if there's any tweaks that I can do. And that's when Gemini suggested two things. One is ZSwap, and the other is ZRAM. ZRAM has to be installed. Both of these are apparently features within the Linux kernel that you just have to enable and configure. And they're not enabled by default for various reasons. ZSwap, it seems like at this point in time, the reason it's not enabled by default is because it's a legacy thing and you don't often need it these days. At least if you're, working with newer hardware, you don't need it. I'm working with incredibly old hardware. So from my understanding, essentially what the ZSwap feature does, which you have to enable it in the kernel, what the ZSwap feature does is as your RAM starts to fill up, or as it's getting to its max limit, what ZSwap is going to do is um, it's going to look at the other processes that you are not currently using. So stuff that's not currently being used by, let's say, the active tab that you have open in Firefox, stuff that's not being used by it, that will all be compressed first of all, and then it's going to be stored in a small allocated section within your RAM, because ZSwap is gonna, or um, whatever is controlling the ZSwap mechanism, it's gonna allocate a certain section. It's gonna reserve a certain section of your RAM that it can use to store these things. Because usually what happens is the way that swap space works is, or swap files, in like the current thing, I believe it's swap files. Previously, you needed swap partitions. You can still do swap partitions if you want, but people recommend swap files. The basic idea is that when your RAM starts to fill up, then the kernel is going to try and use specifically allocated sections on your hard drive as temporary RAM. But because this is allocated on your hard drive, so it's incredibly slow RAM. If we were talking about SSDs, it would probably be slightly faster. But if you're talking about HDDs, like the older mechanical hard drives, it's going to be incredibly slow. The advantage is that your system is not going to crash because you're not going to completely run out of RAM. But the disadvantage is that it's going to be incredibly slow. It's going to be very sluggish. The system is going to be unresponsive at certain times. So it's not the best, right? What ZSwap does is it doesn't store it on the hard disk first. It takes whatever it has to store and it compresses it first, and then it stores it into a specially allocated section within the RAM not within the hard drive. And once that specially allocated section is filled up at some point later, then it's going to go for the hard drive. So the hard drive is the last resort. The advantage of this whole thing is that you end up with a little more RAM to use, or your applications, they have a little more breathing room in terms of RAM. It's not gonna fill up and choke very fast. And it seems like enabling that little feature, even without any specific tweaks to it, just enabling that feature in the kernel has made the system a lot more responsive now. I can actually see an increase in the amount of free RAM available. And just to test it out, I tried loading up a couple of people's streams that I knew I wasn't able to load before, and now I'm able to load those streams. Like that is, dude, this is insane. This is one of those hidden gems in Linux that you it's there if you need it, but you're not always going to be hearing about it. I've been using I've been using Linux for a decade at this point, more than a decade at this point. Never had to touch ZSwap. Well, I would have had to touch it, or I would have touched it much more earlier. I never knew about ZSwap until like today. So I enabled it on this machine, this really old machine, and it definitely helped. Now I'm gonna enable it on a couple of my other machines as well. Like this laptop that I'm streaming to Twitch off of right now. This has a Core i5 8250U CPU. It's a laptop, so it's one of those U CPUs. It's a Core i5 8250. It's got 8 threads, or is it 8 cores? I don't remember. It's not 8 cores. It's eight. It's 8 threads. It's 4 cores and 8 threads. Um, and it's got 6 GB of RAM. So the RAM is a bit of a bottleneck. And I actually did run into some RAM issues when I was trying to stream off of, or but I didn't try streaming, but I tried opening up OBS and setting up the whole workflow there. And I did run into some issues there. So now I want to try enabling this over there, and I want to see how well that works out, because I could definitely use the extra RAM. I want to see to what extent I'm able to like squeeze the most out of it. And who knows, that might help in our transition to Linux, and being able to stream off of Linux. So that would be great. But yeah. So that's what I've been up to. I also, in terms of reading the Forrest Mims Getting Started in Electronics book, I've made more progress. I've gotten to the point where we're learning about DC electrical current, DC as in direct current. And I'm done reading that section. Next, I have to move on to AC. That's a very short section, fortunately. And after that, we are going to be moving on to I forgot what the next section is called, but it basically covers pulses, waves, and things surrounding that. There were 4 specific words for this subject. I don't remember what they were, but yeah, there's pulses and waves and timers and clocks and stuff like that. All of that gets covered in this section. Something that I'm realizing is that this book, it doesn't make you like immediately dive um into the meat of things. It's gradually introducing you to it, but somehow it still manages to keep me interested. Like, we haven't really gotten into doing any practical stuff. Sure, the book has talked about setting up practical examples, practical simple examples. Like there was electroscope, something to detect charge in you know whatever object you're touching. So there was a thing where we could take a positively charged rod, and the electroscope basically has, it's like a glass jar, and there's a cork, and in the center of the cork, you have a copper wire sticking out. And this copper wire, um, so it's sticking out, but then the other end is inside the jar, and it's completely like closed off, and it's like a hook kind of thing. I can actually just show you the image. Hold on for a second. Let me switch to BRB so I can show you an example of an electroscope. Yeah, basically this is it. This is actually more along the lines of what was being demonstrated in the book. I don't know if the exact image is somewhere here. Um, Give me a second. I want to see if I can manage to find it. I do need to be careful because I am on Google Images and, it's Google Images. Nah, you know what? I'm just gonna explain it in terms of this. So, we have this glass jar. Imagine there's a cork at the. Oh, I should also mention. Wait, you guys should be able to see the cursor that I'm moving, right? Hold on. I want to see if the cursor move. Oh yeah, yeah. You can see the cursor. Yeah, there it is. So, this is the image that we are looking at right now. Um. Oh, can I do simple? Okay, let's just go back. So, this second image is what we are looking at. So you have a glass jar. You also have a cork that's at the opening of the jar. So it's basically closing that jar. And then inside the cork, you have you've put a copper wire. Here they're using brass, but they've put a copper wire. Well, in the example that I'm talking about, they've put a copper wire. Um, Sorry, what was I saying? Yeah. So, in the cork, they've put a copper wire. One end of it is sticking outside of the cork, and the other end is inside the jar, and it's kind of like a hook kind of thing. And then you take aluminum foil, and just take one sheet of it and hang it on this thing. Hang it on the hook. Then you take a positively charged rod of some sort, a positively charged plastic rod. Do something to like get the electrons like off of it. Make it mostly positively charged. So then it's got that pull to pull the electrons, and then you bring the rod close to this copper wire. Don't touch it. Bring it close because there's this pull, because the positively charged rod is, it's a positive ion. It has a deficit of electrons, so it starts to pull the electrons from this. And apparently, the effect, what's happening here is that because the aluminum foil and the copper wire are touching together, so they're treated as essentially one entity. And so the electrons, even from the foil, they start to move towards the other end of the copper wire where you've got this positively charged rod close to it. But again, you haven't touched it, so they haven't. So the electrons have no way to get to the other side because there's insulation in between. In this case, the insulation is air. And because of that, you have electrons moving towards that side, but not exactly jumping over. So they're still within this entity. However, because a lot of them have moved towards that side, this foil, both uh, the flaps of the sheet, they end up being a lot more positively charged. And because of that, you have this sort of this repulsion kind of effect where the foil will just kind of like separate by itself. This is my understanding of of what's going on, that the foil basically just repels. The foil's sheets, they repel each other because of their um, positive charge. They're mostly positive charge, and that whole words that whole phenomenon is really interesting to me. That's actually helping me understand the whole idea with protons, electrons, and charges, and also insulators and conductors. All of this stuff is helping me learn the basics that I never actually understood. And that's why I'm continuing to read this book. That's why I'm being patient with it, even though we haven't really gotten into the meat of, building circuits yet. I'm still interested in this. This book is managing to keep my attention and my interest. Dude, I need to do something about this gray screen kind of thing that's happening, because this is not good. Something that I could do, something that I could do. I have no idea how well it's going to work out, but something that I could do is, if I can manage to learn, because I haven't had the chance to continue learning about Wes term because I've been busy, dude. I've been busy with, honestly, this analog electronic stuff. I've been busy, and I haven't had the chance to play around with Wes term a whole lot. Actually, I think what I should do is, I think I should install Wes term on another system, so that I actually have a chance to play around with Wes term. Um, yeah, yeah, I think I should do that. I think I should do that. Because I mean, at this point in time, I'm ready to start using Western. I just wanna I just wanna learn their multiplexing features properly, because there's a bunch of stuff to explore in terms of multiplexing in Western. That's why I kind of wanna explore that whole domain. Speaking of domains, there's a couple of things that I need to explore in Western. There's the concept of workspaces, the concept of domains, because there's different types of domains. You have your local domain, you have a Unix domain, which is basically what you would be using for multiplexing, because Unix domains can persist their GUI window being closed, similar to how tmux sessions work. And then you have SSH domains, which I haven't fully understood the concept there, but my understanding is that these are the domains that you can open them up over the network. So essentially, it's like it's like it's like having a SSH shell. Um, it's basically like SSHing into the machine. However, the tab or the window is going to open up there in Western natively. It's not going to be like, within an SSH shell. That's my understanding, but I haven't had the chance to explore it yet. So that's what I need to explore: the concept of domains, the various types of domains. I need to explore workspaces. I've done a bit of exploration with workspaces. It was interesting to look into because I was able to set up. Hold on. We can close this. Yeah, I was able to set up multiple windows to be part of the same workspace. And something that I noticed is that you have one WesTerm GUI instance running. It's not multiple GUI instances running. However, that one GUI instance that you'll see in BTOP running, that one instance can have multiple windows attached to it. So that one instance can basically have multiple GUI windows, and each of those windows can have multiple tabs within them. And like all of that counts as one workspace. So it's kind of interesting being able to set things up in that way. I don't know what the persistence is like in that scenario, but yeah, it's definitely interesting um, being able to set something up like that. What was I gonna say? Oh yeah. So, another thing that I could do, just to rush getting into WesTerm, just to rush starting using WesTerm. Another thing I could do is, because one thing that's stopping me from using WesTerm right now is it's the me not having learned the multiplexing thing. So what I could do is just not use the multiplexing thing, just not use the multiplexing thing. Um, Wait, give me a second. Okay, yeah. What I could do is I could just not use the multiplexing thing for the time being, and instead I could set up tmux sessions because you can use tmux with WesTerm. It works fine. There might be a tiny bit of a change that I need to do to get um, like the Kitty graphics protocol or any graphics protocol for that matter to work to work in tmux over SSH. There is a tiny setting that I have to do. It works flawlessly with the Kitty terminal, but with WesTerm, I have to do a bit of a setting there. Okay, you know what? We've had a pretty long yap sesh, 37 minutes of yapping. So we're gonna get into this. We're gonna get into LED PWM controller. This time we are armed with the knowledge of how clock signals are generated, um, how clock management works in the ESP32, the various types of clock sources and clock signals that are available, and the logic behind how clock signals and clock sources are used. So this time we should probably have a better idea of what we are doing. Okay, all right. Another thing I'm interested in looking into here is this LED PWM, because it mentions high speed channel and low speed channel. I need to talk to Gemini about which section in the ESP32 TRM, which section explains this LED PWM, high speed channel, low speed channel, and the various timers that are available, and the channels that they can be the words, holy shit, the the channels that they can be split into. Um, I'm Give me a second. Okay, I'm learning about the ESP32, about the ESP32's clock management. Well, no, the ESP32's LED PWM hardware. I'm curious as to which section in the ESP32 TRM mentions um, how this hardware works. I've explored the reset and clock section, um, but that doesn't seem to dive too deep into LED PWM. Any idea? Okay, it makes total sense that you started with the reset and clock section. That's usually the basement, quote unquote, where everything starts. But for the ESP32, the LED PWM functionality is actually handled by a dedicated peripheral with a slightly different name than you might expect. The section you're looking for, the hardware you're looking for is detailed in the LEDC chapter, which stands for LED control. Okay, we're gonna make a duplicate of this and go down to third. Wait, I duplicated the wrong thing. We're gonna make a duplicate of this. Dude, it might be my network because even this PDF is loading really, really slow. It might be my network. Anyways, okay, wait. What? How is layers? Let me select the damn thing. Oh, these are the layers. Wait, no, they're not the layers. This cannot display it in layers. Okay, all right, never mind. We are on chapter 7. Yeah, we're on chapter 7. We're supposed to go to chapter 13. Also, what are we in right now? Because it says here 3 system component, but then it's chapter 6, and then prior to that is chapter 5. Where's that scrolling thing? Here. Oh, okay, you know what? I guess that's just their way of yeah, yeah, okay, that's just their way of um kind of categorizing the various um sections, the various topics, categorizing the various topics. Okay. All right, so we are supposed to go to 13, which is process ID controller. Is that right? Chapter 13, process ID controller. No, I don't think I think Gemini is mistaken here. Let's go to LEDC. Let's see if anything pops up. I need to go all the way to the beginning. Okay, clock derivation, PWM controller. Chapter 28. That is crazy. Okay, all right. Um, oh, here it is. This is the architecture. PWM, high-speed channel diagram. All of this is mentioned in well, a lot of these diagrams, I should say, not all of this, but like a lot of these diagrams are mentioned. Um, so like you have this first of all, and then you have the signals thing was mentioned somewhere, either here or maybe in the previous section. Maybe it was mentioned in PWM in depth, or maybe it's mentioned in fading LED. That's a possibility as well. Okay, all right. Give me a second. Let me hydrate. Let me also drink some of my energy drink, and then we will continue. Okay. All right. So we are looking now into this. So there's a couple of things that we need to explore here, right? And maybe the divider is also going to be mentioned. Maybe the divider is also going to be mentioned here, because it does mention LED PWM divider. So that's why I was like, maybe the clock divider will be mentioned here. Um, okay, we can probably maybe I could close this because this is probably going to be a different section. Yeah, it says it has two PWM peripherals. One is the LED controller and one is the MC PWM controller. I keep having to do the alt tab thing. Well, not alt tab, but like control page up. I'm switching tabs each time, and it's an extra step that I have to take to get back to this section, and I kind of want to bounce between the two. Okay, so wait, I mean, do we should we bother with this or just start reading from here? Timers, the clock of each high-speed timer. We could just read this. And okay, this looks similar to yeah, these two formulas look similar because I'm seeing clock div, which is I was wondering where the clock divider comes from. And then this is LEDC clock. I'm guessing that's a register that's being whose value is being set based on something. Um, wait, give me a second. Okay, all right. Yeah, let's just read this. Okay, introduction. LED PWM controller introduction. The LED PWM controller is primarily designed to control the intensity of LEDs, although it can be used to generate PWM signals for other purposes as well. Okay, it has 16 channels which can generate independent waveforms that can be used to drive RGB LED devices. All right. For maximum flexibility, the for maximum flexibility, the high speed as well as the low speed channels can be driven from one of four high speed slash low speed timers. Okay. I'm trying to like visualize that, but I think that's visualized down here because they said one of four. So both high speed and low speed. Initially, when I read that, I was like, oh, are the timers like interchangeable? But no, they're not. You have H timer. So H timer 0, H timer 1, 2, and 3, and then L timer 0, 1, 2, and 3. I need to look into what this channel thing is. Is it just like a separate path that you can send out the signal to? And like we have 16 here, but like what output pins are they coming out of? Like this lets us generate so many different signals, right? How are we actually getting this out of the ESP32? Do we need to use separate hardware for this, or like what's the situation there? Because I do also have. I should look into if shift registers would be useful for something like this. I don't know what the timing situation would be for shift registers, but yeah, that would be interesting to look into. Also, the fact that they have all of this, they have all these so many different options. This is giving me ideas for setting up. So okay, I had this idea, this project idea in mind where I would write a Rust program that would capture what? Oh, I would write a Rust program that would capture the pixels of your screen and or basically read the pixels that are currently on the screen, and then based on that I would change the colors of the LED strips that were connected. So basically it could be like an audio, not an audio, a light reactive, what do you even call it, opto reactive. um, it's a reactive light. So let's say if you're watching a video, then you can have like the colors from the video being displayed through the LEDs in your physical space. I have an LED strip that came with an LED driver. This is one of those cheap LED strips, which is actually great. Like, I'm saying cheap as if it's a bad thing, but it's not a bad thing. Or, well, I'm saying cheap and it sounds like I'm saying that it's a bad thing, but it's not a bad thing. It's one of those cheap LED strips that you can get from some discount store, and um, it comes with an LED driver, which has, well, okay, it comes with an LED driver and an adapter to power that driver along with the LED strips, and that driver also has um, it has a infrared receiver. So you also get a remote along with that. So that remote lets you choose between different lighting modes and specific colors and stuff like that. That entire chip has been designed to allow you to use this remote and use specific lighting modes and specific lighting colors. It's all pre-programmed. I would show you the remote, but I don't have. I mean, I'll have to get up and go get the remote. I mean, I'm talking about the thing, so I might. Nah, I'll have to get up and go get it, and then show the thing here, and then I'm gonna start talking about. You know what? No, I'm gonna get it. Wait, hold on. Okay. So this is the driver. Um, I need to make sure you guys can see it. Hold on. Um, Here. This is the driver. You can, here is the infrared receiver. That's this white wire. And then this is what you connect into the LED strip. You have you have four wires here. So there's RGB and black. Black is for ground. Um, Also, this is where the adapter gets connected in this driver. This is the remote. Yeah, this is the remote, and you can see a bunch of different buttons on here. There's buttons for different lighting modes, like blinking and I don't know, fading and stuff like that. There's also buttons for setting the entire LED strip to like specific colors. So it's kind of interesting. You can use this to, um, what was I saying? Oh yeah, you can use this to do interesting things with this with the LED strip. However, you are limited in terms of oh yeah, sorry, just lost my words there. You are limited in terms of what you can do, like in terms of customizability. You can only do whatever this remote allows you to do. That's all you can do. You can't really do anything past that point. That's what the circuit has been made for. That's what this remote has been made for. Actually, speaking of which, um, I could probably use this remote for some other purpose. I just realized that because this is basically a remote. This is a remote. This is a remote. It's not basically a remote. This is a remote. Um, I could build something that responds to the infrared signals that this is putting out, and just like that, I have my own remote. Or I could just change the IC. Oh wait, no, that's probably like embedded. Yeah, maybe I can't change the IC. I could decode the signals of this remote though. That would be interesting because I do have some infrared related modules. I never got them to work, but then to be fair, I didn't really know too much about what I was doing um, in terms of both the ADC and the DAC. So like sending and receiving, I wasn't really too familiar with what I was doing. And now, like learning all of this PWM stuff, now I know for sure that I had absolutely no idea what I was doing back then. And so there's a pretty decent chance that it didn't work because I didn't know what I was doing. It's not that the hardware is damaged. It's not that I received damaged goods. It's that I literally did not know what I was doing. Um, but yeah, okay. So my idea was to basically, because okay, this uh, LED driver, this LED driver, it's pretty decent. I mean, aside from, the very limited functionality, something else good that it does is that it gives us something to be able to power the LED strip. So I think it's a 12-volt adapter that came with this set. This is what I was saying. Like, this is nice and cheap, and it's great for the price that you're getting. I don't know if it's the best quality stuff, but it's if what you get is functional, that's it. That's all you need. It's not like gonna you're gonna run this for the next 5, 10 years or whatever. I mean, I shouldn't say that. Like maybe somebody has plans to do that. Maybe in that case you wanna go for higher quality stuff. But honestly, like if you're getting cheap LED strips, um, then for immediate things that you have to do, quick projects and stuff like that, it's amazing. I personally would go for cheaper LED strips. Anyways, back to what I was saying. This is great. This LED driver is great. It's also an RGB, specifically an RGB LED driver. This thing takes it takes DC 12 volts, and it can output 6 amps max. And I got the adapter with it as well, like the adapter to power the thing. So in terms of power, we are good, right? All I need to do is, let me see if I can open this. Like, I don't remember if there was screws here or like what was the situation. Give me a second. Sorry, that might be loud on stream. Okay, yeah, it's just clips. Oh, it's one of those project boards. Yeah, I actually ordered one of these. This uh basically it's this. I ordered not one. I ordered a couple of these. This is what the circuitry looks like. So on here, I don't know how well you can see, but there is an IC. Oh yeah, I think you can see it. I think you can see it. It's in the center of the board. There's an IC that is responsible for all of this stuff, all of the lighting related stuff. What I want to do is I want to hack this circuit and bypass that IC and thereby bypass the entire infrared functionality so that I can interface with this using my ESP32. The thing is, as usual with me, I'm not comfortable with mixing high power and low power circuits, high voltage and low voltage circuits, high current and low current circuits. I'm not comfortable with that at all. And if I want to control this circuit using an ESP32, more specifically, if I want to have fine control over it, over each of the colors, I would need transistors. And using transistors means I need to combine the ESP32 circuit with this circuit, and I'm not comfortable with doing that. So I want to try my best to use optocouplers for I don't know if that gray screen thing is gone yet. So I mean, I feel like it's still occurring every now and then. Let me see if it's still occurring. If it's still occurring, then I'll just get rid of that network caching thing that I had set. It was previously set to 100 milliseconds. I cranked it up, hoping that it would, get rid of this gray screen issue, but it still seems to be occurring every now and then. Though, okay, something worth exploring for me is whether it has lessened that issue. Like, is the issue still like um, how often is it occurring? That's something I need to explore. Okay. Um, sorry, zoned out. Okay. My project idea here is that so we definitely need transistors. There are transistors on this board, this chip that I just showed you. There are already transistors there, but I don't know too much about them, so I don't wanna use them. I have my own BJT transistors. I'll use those instead. Actually, now that I think about it, maybe I should use this. Should words? Maybe I should try to use these transistors because these transistors are made specifically for this purpose, or these not made. They've been picked specifically for this purpose, right? So even if they're some of the more general purpose transistors that just happen to fit this use case, they fit this use case. Like that's end of the story, right? They fit the use case, so I can use them. I need to make sure that these are transistors. I think these are transistors. I'm pretty sure these are transistors because it's not the IC that's powering. Sorry, it's not the IC that's powering the um it's not the IC that's powering the LED strips. So it has to be transistors. The IC is going to be the IC is essentially a microcontroller. It's like a purpose-built microcontroller. It's not a general purpose microcontroller, but um, this IC, I can show it on screen here. This IC is um, I'm sure it's putting out small signals which are being sent into um, the base of the transistor. And actually, yeah, that just made me realize I don't even know if this. Oh God, dude, the latency is crazy. What is going on? The latency is wild. Actually, I did set it to be that high. Though I don't think. Wait, let me just. Okay, I handled that kind of. Yeah, yeah, it's like a 2 second latency now. Okay. Yeah, I just realized that I am not even sure if these are BJTs or if they are what do you call it? I'm not even sure if these are BJTs or they are MOSFETs, because BJTs are current controlled transistors. MOSFETs are voltage controlled. Dude, hold up. If they happen to be voltage controlled transistor, well, okay, with an optocoupler, I can't um, control the voltage. I can control the current. I can't change the voltage that's being passed in. I just refresh this, and now there's a gray screen thing coming up. Okay, yeah. So, um, I might have to stick with BJTs because with a microcontroller, I could put out different voltage levels using, I'm assuming, using the DAC. But sorry, I'm just looking at something. Yeah. Um yeah, with where was I even going with this? Yeah, I need to find out if these are, because this just occurred to me that I don't know where like the microcontroller seems to be sending signals to each of the transistors, right? But then I'm not sure what type of transistor this is. Granted, I mean, it could be actually, if it's a digital to analog converter, are we also able to control the current? With a digital to analog converter, we can control the voltage level. Is controlling the current a thing? Because we don't really control the current when we are controlling an LED. Like if we are trying to do like a fading kind of effect, that's more an illusion and less of a, current limiting kind of thing. We're not actually limiting the current. We are pulsing the LED on and off so often that it looks like, it's dim or lit up. Actually, I forgot what the illusion was exactly. Like, yeah, I need to revisit that. Like, is it that a smaller number of I think okay, I'm trying to think that in PWM, are we controlling the voltage or the current? Because yeah, we are pulsing it, and the dimming effect, it only happens because it only happens because we are creating that illusion by pulsing a lot, right? But then, is the pulse always the same? Because it's between 0 and 1, right? The pulse is between 0 and 1. What we are changing is not the level of the pulse. We are changing the amount of pulses, and that is creating the illusion, right? I can't remember. Sorry, I we read up on PWM a while back, and I've already like forgotten what that whole thing was. I guess we can like revisit that. But yeah, speaking of PWM, we're supposed to be reading this. Okay, up here. Okay, for maximum flexibility, the high speed as well as the low speed channels can be driven. Okay, these are channels. The channels are also low speed and high speed. I didn't pay attention to that. Okay, okay. Like the channels are also being categorized as low speed and high speed. So in total, we have 16 channels, 8 on high and 8 on low, right? Let's read that from the beginning again. So the LED PWM controller is primarily designed to control the intensity of LEDs, although it can be used to generate PWM signals for other purposes as well. Sorry, zoned out. Okay. Um, what was I talking about? Oh, I was reading this. Okay. It has 16 channels which can generate independent waveforms that can be used to drive RGB LED devices. This says waveforms, but no, it's PWM. It's PWM. Okay. Though I mean, yeah, PWM is also a waveform. It's mainly it's a square wave, right? Yeah, yeah, it's a square. Holy shit, dude! I've completely forgotten PWM. Um, PWM in depth. Timer operation, compare value. Okay, okay. All right. So this is our thing. This is the whole counter thing. How it's measuring time. I actually forgot about this as well. Holy shit! We need to revisit this stuff as well, because this is how it's creating the notion of time. Sorry, zoned out. Okay. Um, we need to go one step back. Right. What is PWM? PWM stands for so and so. Okay, 10% duty cycle. So it's basically just on and off. We are not controlling the level. The level is either 0 or 1. So that part is digital. That part is binary. However, what we are controlling is the duration of how long it remains on. And because of this constant pulsing for this specific duration, um, every cycle, um, we are able to create this this illusion. So that's what's happening. We need to, holy shit, we need to practice this like so much more before before the before that whole idea kind of like sticks in my head. Okay, it has 16 channels which can generate so and so. Okay, all right. For maximum flexibility, the high speed as well as the low speed channels can be driven from one of four high speed slash low speed timers. The PWM controller also has the ability to automatically increase or decrease the duty cycle gradually. The PWM controller also has the ability to automatically increase or decrease, gradually allowing for fades without any processor interference. To increase resolution, the LED underscore PWM controller is also able to dither between two values when a fractional PWM value is configured. I haven't fully understood that part. I'll explore that a little bit later. Okay, the LED PWM controller has 8 high speed and 8 low speed PWM generators. Okay, that's what the channels are doing. Okay, so it's 8, it's 16 in total independent PWM generators that we have. In this document, they will be referred to as, oh God, as H, oh, high speed channel N, high speed and low speed channel N, respectively. These channels can be driven from 4 timers, which will be indicated by by H timer X, and oh, N is supposed to be the number. All right. And then X is also supposed to be the number. All right. Okay. Functional description. Architecture. Figure point four. What did I just say? Figure so and so shows the architecture of the LED PWM controller. As can be seen in the figure, the LED PWM controller contains 8 high-speed and 8 low-speed channels. There are 4 high-speed clock modules and 4 high-speed clock modules for the high-speed channels, from which one H timer X can be selected. There are also 4 low-speed clock modules for the low-speed channels, from which one L timer X can be selected. Okay. Um, then LED PWM high-speed channel diagram. So what are we looking at here? I think I need to zoom in for this. H timer and then H channel. Okay, so this is the mux, I'm assuming, that decides. Yeah, it says LED tick selector HS timer. So this is gonna decide whether it's using ref tick or APB clock, and then it gets passed into a fractional divider, which is set by LED clock div num HS timer X. Okay. Then from the fractional divider, we are going to the counter. So what's happening here? I didn't understand this part. So fractional divider, oh, this divides the tick that we are getting, and that passes it into the counter. And then from the counter, we are sending a ref pulse over to this section. We have high level comparator, low level comparator. This is all for the high speed, right? This is not for low speed. Yeah, this is the high speed channel diagram. High speed channel. That is here. H channel. Oh, that is here. This is the entire high speed channel. So we have timer mux channel, right? So here we have the H timer and we have the H channel. LEDC H point HSCH. Okay, high level compared. I guess this is where the comparator is used to decide at what point it is supposed to be high and what point it's supposed to be low, right? Why do we have two separate comparators for high level and low level? I think I need to go back to like that whole wait, these two things are coming in here. Is there a description? Is there a explanation for how this is supposed to work? I feel like I need some time to understand this. Yeah, I feel like I need to like look at this for some time to wrap my head around it. Okay, the clock for each high-speed timer. Wait, is it mentioned here maybe? No. We need to try and get it ourselves. Okay, the clock of each high-speed timer, LEDC clock X, has two clock sources, ref tick or APB clock. For more information on the clock sources, please see chapter Reset and Clock. All right. The input clock is divided down by a divider first. The division factor is specified by LEDC clock div so and so, which contains a fixed point number. The highest 10 bits represent the integer portion A, while the lowest 8 bits, this is the highest 10 bits, and the lowest 8 bits um, contain the fractional portion B. Okay, the effective division factor, LEDC clock div, is as follows. The division factor ranges from 1 to 1023. When the fractional part B, dude, I'm going to be honest, I'm barely grasping what I'm reading here, and it's because I haven't eaten very well. I also haven't slept very well. Holy shit, dude. I need, or maybe it's just that I'm um, absorbing way too much information and I maybe need a break from this. But it's the thing is I don't want to step away from this because it's getting really interesting. Um but yeah, I mean if we are learning about PWM, then we're gonna, have to go through this whole thing and oh, this is the table that's being shown here. Yeah, this is the table. Commonly used PWM frequencies and resolutions. You know what? Maybe I might not even need to. I mean, I would still try and understand the math behind it. But then, yeah, we might not really need to do the math each time. Probably not. Then we have the channels. Yeah, yeah. Okay. So there's a lot for us to explore here. And yeah, dude. I think I'll end the stream here. We'll continue reading up on this tomorrow. Definitely, we're gonna continue reading up on this tomorrow. I'm gonna end the stream here, and I I have to look into this gray screen thing. So far, it's not like that bad, but like it's annoying that every now and then it pops up. But I guess it is what it is. I also am now realizing that the feed is stuck. It is not displaying the feed. Okay, now it's better. Yeah. I need to look into this. I also need to continue with reading my reading up on analog electronics because I'm making good progress. So far, I'm on page 17, which is awesome. I'm hoping to get through a bunch of the pages today and get into the more interesting portions of that book. But yeah, that's going to be it for today's stream.